Hello, welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'll be your moderator for today. I'm Steve Haneke, Assistant Professor of Computer Science at Purdue University, and also an ACM member. My research focuses on the theory of machine learning. For more on my background, you can check out the bio widget on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, as well as the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Okay, before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. If you have questions at any time, please type them into the Q&A box and click submit. I'll organize the questions for Nina as she speaks, and we'll try to get to as many as possible. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our tech talks. You may also open the link to the survey at any time from the resources window. Okay, now we should all be very excited because today's presentation is Machine Learning for Algorithm Design by Maria Florina Balcan, or Nina as she's known to most of us. Maria Florina Balcan is the Cadence Design Systems Professor of Computer Science in the School of Computer Science at Carnegie Mellon University. Her main research interests are machine learning, artificial intelligence, theory of computing, and algorithmic game theory. She is the recipient of the ACM Grace Murray Hopper Award. She's a Simons Investigator, a Sloan Fellow, a Microsoft Research New Faculty Fellow. She received the NSF Career Award and several Best Paper Awards. She has co-chaired most of the major conferences in the field of machine learning, the Conference on Learning Theory, the International Conference on Machine Learning, the Conference Neural Information Processing Systems. She was also the general chair for the International Conference on Machine Learning, a board member of the International Machine Learning Society, and a co-organizer for the Simons Semester on Foundations of Machine Learning. And while all this is all very impressive, of course, even more so is the brilliance of her work. In her research, she's made profound contributions, both in laying the theoretical foundations for core topics in machine learning, things like semi-supervised learning, active learning, clustering, computationally efficient learning in noisy settings, and so on, as well as in broadening the scope of the field, exporting machine learning perspectives and principles to make important advances in other subjects, such as algorithmic economics and data-driven algorithm design. I know we're all looking forward to hearing her talk about some of this work today. So without further ado, let's welcome Nina.
Thank you, Steve, for the introduction. Can you see me well? Yeah, great. And let me know if you can see as I push through the slides. Okay, great. So my talk is about using machine learning for algorithm design, also known as data-driven or automated algorithm design. Now, can you see that I pushed the slide already?
Yes.
Great. So, and let me start with a high-level overview of my talk. So first of all, I'll be thinking about learning algorithms for solving algorithmic or optimization problems that involve discrete or combinatorial structures where the inputs or the outputs might be combinatorial. So for example, the problem of clustering or organizing an input set of items into natural groups, or the problem of pricing a given set of items in order to maximize revenue. Now, such problems, and in fact, most combinatorial problems, are hard within the classic analysis frameworks. So Steve, can you confirm it? You can see me pushing the slides?
Yes, I see them.
Great. And the audience sees them already. Great. So such problems like clustering problems, pricing problems, and in fact most combinatorial problems are hard within the classic analysis frameworks. Now, in these classic frameworks, we assume that the algorithm designer designs the algorithm analytically by hand. So the algorithm is actually hand designed. And from an analysis point of view, we impose that the algorithm must succeed even on worst case instances. That is, for solving even just a one-shot, worst-case instance of the underlying algorithmic problem. Now, while this framework has been the backbone of algorithmic research and applications since the field's inception, unfortunately, for many problems, the types of guarantees we can obtain within this classic algorithmic framework are actually often quite weak, either for running time or for solution quality or for other performance measures. And as a consequence, rather than using hand-designed algorithms with only weak worst-case guarantees, it has become increasingly common across many different fields to use a data-driven algorithm design approach. Okay, that means we consider large families of parameterized algorithms, and we use machine learning and instances of the problem coming from our specific domain in order to learn an algorithm that has well on instances coming from our given domain. Now, this idea has been already used across different fields, ranging from artificial intelligence to computational biology to game theory. And actually, some of the breakthroughs in these fields are due to this approach. However, surprisingly, in my opinion, until very recently, there has been very little foundational understanding, theoretical understanding, asking about what kind of guarantees we can hope to provide for these data-driven algorithms. Okay, and today in my talk, I'll tell you about work in my group over the past few years with my students and collaborators on using machine learning and learning theory lenses to provide strong performance guarantees for this data-driven algorithm design approach. And I'll mention both case studies and general principles for analyzing data-driven algorithms by using both a statistical or distributional and online learning formalization of the problem. Okay, and so I also want to point out actually that this line of work simultaneously pushes the boundaries of algorithm analysis and design because it provides principal analysis tools for these data-driven algorithms. But it also pushes the boundaries of machine learning because now we consider learning much more complex objects beyond simple classifiers as typically done in machine learning. Great. So this was the introduction, the high-level overview of the talk, and now I'll go ahead and try to become a bit more concrete. And I'll start in particular by discussing data-driven algorithm design as a statistical learning problem. But before doing so, before presenting actually a model, I would like to make things a bit more concrete, and I'll just mention one concrete example of a hard combinatorial problem that we might want to solve in this data-driven by using the data-driven algorithm design approach. Okay, this is clustering, problem that hopefully many of you are familiar with. So, so we are given a set S of n points or objects, such as images, maybe news articles, web pages, and we are trying to, and our goal is then to organize them into, as best as possible, into natural groups. Okay, and notice that actually we often need to repeatedly solve instances of such problems, instances of clustering problems. So for example, if I'm using clustering to organize news articles, like some, like for example, Google News does, we might need to cluster news articles repeatedly every day, in fact, many times a day. Now, technically, so this is what the clustering problem is about. Now, technically, how do we solve it? There are several ways to solve it. One of them would be to consider an objective-based formulation of the clustering problem, where we pick a very specific objective function like k-means or k-median and try to optimize it. So, for example, one of the most popular objectives across many fields, including machine learning, is the k-means clustering objective, where which can be described as follows. So the input to our problem is a set S of an object of endpoints and distances between these points. And then the output is a partition of these points and centers for each part of the partition in order to minimize the sum of all points of the distance squared to the nearest center. Okay, so this is a classic k-means clustering objective. And as you might know, this is an NP-hard, so optimizing this objective is NP-hard. The same is true for other related objectives like k-median and k-center. So they're all good applications of the data-driven algorithm design approach. Because we cannot hope to design, because they are NP-hard to optimize, we cannot hope to design algorithms that work well on worst-case instances. So it's natural to try to learn an algorithm for our type of instances. Okay, so one formulation of the clustering problem is the objective-based clustering problem, but we can also consider a more unsupervised learning or matching of the ground truth formulation, where we assume that there is somehow some true unknown ground truth clustering of these points, maybe the way Steve would cluster these images by content. And then our goal is to try to output a clustering that is close to that ground truth clustering. Okay, this is a more unsupervised learning formulation, but it's also really hard in classic frameworks. So again, a good approach is to try to learn an algorithm for this problem in a data-driven way. Okay, now with this example in mind, with the clustering problem as an example in mind, I'm now ready to tell you how we can think about data-driven algorithm design or selection as a distributional or statistical or batch machine learning problem. And at the very high level, the basic idea is as follows. And by the way, if you are familiar with machine learning, this will be incredibly natural. So it's very natural formalization. So here's our high-level idea. So we first fix a combinatorial problem that we want to solve. And this can be a clustering problem, a facility location problem, your favorite algorithmic problem. Okay, and then we also fix a large family of algorithms that are either commonly used in practice or that we somehow hope or we have analytical reasons to believe that they will turn very be good for our given problem. Okay, we then take a collection of typical problem instances coming from our domain, and formally we will assume that these problem instances are instances drawn IID, that means independent, identically distributed instances from a fixed unknown distribution of a typical clustering of a typical problem instances. Okay, and then what we'll do, we'll use this collection of typical problem instances coming from our specific domain in order to find an algorithm from this fixed family of algorithms that we hope or want to prove that there's all new instances coming from the exact same domain, from the exact same distribution of our typical instances as a training set of typical instances. Okay, so let me say this again more slowly. So let me go this more slowly. So we first fix a problem that we want to solve, say a clustering problem or a facility location problem. Then we fix a large family of algorithms for our problem. And these algorithms could have your favorite components, like algorithmic components, like dynamic programming, greedy components. Yeah, we can have your favorite components, right? And then actually this family of algorithms could even be infinite because some of these components might have some knobs or real valued parameters that we might hope to somehow tune based on data. Okay, so we fix the problem that we want to solve, and we fix a large, infinite, potentially infinite parameterized family of algorithms for our problem. And then what we do, we take a set of typical instances coming from our domain. So for example, if we're trying to do, say, a facility location problem, where the inputs are graphs, here at the bottom, you can see how our typical instances might look like, right? So we might have the first typical instance will be an input graph 1, the second typical instance will be an input graph 2, and so on. We have capital N such typical instances that come from our given application domain. Or this is for facility location, or if we're trying to learn how to cluster, here again, I have on my slide examples of how the typical instances might look like. So here I'm looking at clustering images by content. So here I might have a typical instance 1, a set of images, another typical instance is 2, another subset of images, and so on. I have capital N such typical instances. Right, and for clustering, depending on the formulation that I use, some of these instances will be labeled or unlabeled. So if I'm trying to learn an algorithm to solve the k-means clustering problem, which is objective-based formulation, then the instances will be unlabeled. But if I'm trying to learn to cluster, if I'm using the more unsupervised learning formulation of the clustering problem, where I'm trying to, say, learn to cluster how Steve clusters these images by content, then I need to ask Steve to basically label for me, to sit down and provide me the target clusterings for this training set of clustering problems. Okay, so basically, so again, we fix a problem that we want to solve. We fix a large parameterized, potentially infinite family of algorithms for our problem. We then take a set of typical instances coming from our specific domain, and then we use this set of typical instances in order to find an algorithm that we hope will do well on new instances coming from the same domain. Okay, so from a machine learning point of view, if you're familiar with machine learning, all we did was just phrase machine learning as a statistical or distributional learning formulation. So just phrase algorithm design as a statistical or distributional learning problem. The only difference is now the instances are just these more complex inputs. For example, graphs for learning how to solve the facility location problem, or like sets of images if I'm trying to learn how to cluster images by content, right? So we just phrase the algorithm design as a statistical learning problem, and so then a very natural formulation to solve this problem, a very natural approach to solve this problem, given that we phrase it as a statistical or distributional learning problem, a very natural approach to do so is to do what we always do in machine learning, what we call empirical risk minimization. So it's just natural to find an algorithm, a hat from our fixed parameterized family of algorithms that does well over the training set of typical instances, right? So that's a very natural approach. What else could we do? We're going to try to find an algorithm from our large infinite family of algorithms that does as well as that is optimal or maybe nearly optimal in a well-defined sense over our training set of typical instances. Okay, now this makes a lot of sense, of course, but the key question is, do we get any generalization guarantees? Right? In other words, this algorithm that does well over the training set of typical instances, will this algorithm generalize? Will it do well on new instances that come from the same domain, from the same distribution as a training set of typical instances? Okay, and more concretely, to make this even more formal, we can ask, will this algorithm I had, which is nearly optimal over the training set of typical instances, will this algorithm I had do nearly as well as the best algorithm from our fixed family of algorithms with respect to the fixed unknown distribution over typical instances from which we had a training set of typical instances? Okay, this is what we mean by generalization, right? And so more concretely, also I have here pictorially, like for the clustering problem, which I had used as an example, we know that the algorithm I had will do well on the training set of typical instances, right? Because we've chosen it to do well, to be a nearly optimal algorithm on average over the training set of typical instances. But of course, what we really care about, the key question here is whether this algorithm I had will also dwell on new instances coming from the same distribution that we have not seen yet. And moreover, we want to know what fraction of those instances will do any good. Now, if you think about it, well, the answer to this question will depend on how many training typical instances we have seen in the training phase, right? Because if we see very few training instances, there is no hope to generalize, but as we see more and more, there is more and more hope to generalize. And so basically in this context, a key question is what we call in machine learning a sample complexity question, which asks how large should our sample of typical instances be in order to guarantee that good performance over the training set of typical instances translates to good performance on new instances as well. Okay, so that's a key question that we have to address if we want to understand the general, whether these algorithms will generalize or not. And the cool fact is actually that we can use tools from statistical learning theory in order to we can build on tools we can build on and extend tools from statistical learning theory in order to provide generalization guarantees for these settings and to answer the sample complexity questions in this context. Okay, and now what do we know? We know from learning theory, and this is slightly technical, but I'm going to try to describe it at a high level. So we know from a learning theory that if we are able to somehow bound the intrinsic complexity of our family of algorithms, in a learning theoretic sense speaking, right? So if we're able to somehow bound this intrinsic complexity, which I denote on my slide as dimension of the family of algorithms. So if we're able to bound this intrinsic complexity, then we can immediately provide so-called uniform convergence bounds, which roughly speaking quantify how many typical instances suffice to guarantee uniform convergence and good generalization, right? So again, what are these uniform convergence bounds? They are bound on the number of samples that we need to see in the training phase in order to guarantee that with high probability over the draw of the random sample of typical instances, we now have it uniformly for all the algorithms in this family that we fixed of algorithms. We have it uniformly for all such algorithms in our class. We have that the average performance of any such algorithm is close to the expected performance on over the underlying distribution, or new random instances coming from the same distribution as a training set of typical instances. Okay, and these uniform convergence bounds are great. So once you have enough samples to get uniform convergence, this is great because if you think about it, this then immediately implies that this approach, where this ERM approach that we talked about, where you find an algorithm that does all over the training set on average over the training set of typical instances, this approach will lead to an algorithm that generalizes, that will have high expected performance. Okay, so it's sufficient basically to get enough samples to guarantee uniform convergence over our family of algorithms. And now the key quantity, so without going, I'm not going to try to define it, but I'm going to try to describe it intuitively. Now the key quantity in this uniform convergence bounds is somehow this intrinsic dimension of the family of algorithms at hand. Okay, and then which we can then use to get bounds at this form, which says that if the number of training samples we see is of this order, well, dimension of f over epsilon squared, that's sufficient to get epsilon generalization. Okay, and again, I'm not going to define it formally, but just want to tell you intuitively what this notion of dimension means. It's roughly speaking, what these notions of dimensions, there are several of them. In our work, we use pseudo-dimension. And roughly speaking, what they quantify is kind of the ability of the functions in our function class at hand to fit complex patterns, right? Because the more complex patterns you can fit, like on many instances, the more samples you somehow need to generalize, right? This is the high-level intuition. It roughly quantifies on how many samples can we fit kind of very complex patterns, because if we fit really complex patterns, we might be in a situation where we have two very different looking functions that, or two functions that look the same on the training set of typical instances, but very different on any future instance. That's of course not good because we don't generalize. But the good news that we can show that if the dimension of the function class is small, this behavior is not going to happen, right? So then we are able to generalize. Okay, so that's just again to summarize, just really for the purpose of this high-level audience talk, all we need to know that these notions of dimensions kind of try to quantify the ability of the function in our function class to fit complex patterns. And they exist already in learning theory, and we can build on them. And we can use them in our sample complexity bounds to talk about generalization for our data-driven algorithm design problem. Now, the key problem is, the key challenge is when we try to use these notions of dimensions in the context of data-driven algorithm design, is that actually suddenly we have much more complex function classes that we need to understand, right? So, in particular, the function class that we have to understand is the function class induced by algorithmic families with respect to our desired performance measure at hand, like running time, solution quality, and so on. And so it turns out, as you'll see in my talk, that kind of if we think about the function classes coming from the data-driven algorithm design context, they have a much more challenging structure than what they typically see in machine learning. In particular, they can have many sharp transition boundaries, like in these pictures here. These are concrete examples from our case studies. Right? And the key challenge intuitively, why do we have so many sharp transition boundaries? Well, because the key challenge is because at a very high level, kind of the inputs are combinatorial, the outputs might be combinatorial, the inputs might be combinatorial, the outputs might be combinatorial, our algorithms have combinatorial modules, and because of this, we can be in a situation where slight changes to the parameters of the underlying algorithms will lead to completely different kind of behaviors, completely different outputs on the given problem, right? So that's why we can have such many sharp transition boundaries. So the loss functions kind of are very volatile. So that's one major challenge that we have to address. And another major challenge, of course, we also want to address is, well, we want to implement this ERM approach. We want to find an algorithm that does it over a training set of typical instances, hopefully, of course, in polynomial time. Okay, so these are the two major challenges that we need to address in this context, and we are able to do so. But before telling you about our results, I want to point out that, first of all, this idea of phrasing data-driven algorithm design as a statistical learning problem has been first introduced in a paper by Rishi Gupta and Tim Rapkardan in ITCS 2016. There they proposed the model, and they also analyzed several families of greedy algorithms for subset selection problems like knapsack and maximum weighted independent set. And following that work, actually, we then analyzed with my groups, my group with my amazing students and my amazing collaborators, were able to analyze many new algorithm classes applicable to a wide range of problems, relevant to many fields like clustering, alignment, auctions, and so on. And not only were we able to provide specific analysis for specific function classes, but we were able to also extract very general principles about how do you analyze the sample complexity for your favorite data-driven algorithm design problem. So, which I think will help us put this field kind of on solid foundations and hopefully become very widely used. Okay. So I guess some of the slides have not the best view here, but I guess we'll be fine. Only some references are a little bit not perfectly showing up here. Okay, now let me go and tell you a concrete result. So for the rest of my talk, I want to tell you a concrete result about data-driven algorithm design in the context of clustering problems, and also tell you a little bit about our general sample complexity results. Okay, in order to talk about data-driven algorithm design for clustering problems, the very first thing we need to put down is a family of algorithms. Okay, and in our work, we consider a family of algorithms that is widely used in practice, is a family of polynomial time two-stage algorithms, where we first organize the data that we want to cluster, like, say, in this case, images. We first organize this data into a hierarchy or tree of clusters by using somehow a fast, greedy approach, bottom-up approach, linkage approach. Okay, and then in the second phase, we use a fixed procedure, say dynamic programming, in order to extract a good pruning according to our desired measure. Okay, and notice that both of these steps can be done very efficiently, and that's why they are widely used in practice. Okay, and just to remind you, or if you've never seen these kind of bottom-up procedures for organizing the data into a hierarchy, basically they are very simple greedy procedures where we start with each point, initially in some little sub-cluster, and then we repeatedly merge the two closest clusters until we get a hierarchy. Now, different notions of closest, what I'm saying we repeatedly merge the two closest clusters. What do I mean by this? Of course, different notions of closest will give rise to different algorithms. And so, for example, So for example, single linkage criteria defines distance between two subsets A and B to be the minimum distance between points in those subsets. And complete linkage defines the distance between two clusters or subsets A and B to be the maximum distance between points in those two subsets. Okay, these are standard kind of textbook linkage criteria. But of course, you can also imagine interpolating between these standard criteria, and then we can get infinitely many algorithms because we can weigh different linkage criteria differently, producing a whole spectrum of algorithms. Okay, so for example, one family of algorithms that we analyze in our work is what we call alpha-weighted linkage, where we interpolate linearly between single and complete linkage. Right, so in other words, there is this unknown parameter alpha, and that we can try to tune based on data, and then we define the distance parameterized by alpha between sets A and B to be 1 minus alpha times the distance between given by single linkage plus alpha times the distance given by complete linkage. Okay, so this is, for example, here is we have written down a parameterized infinite family of linkage procedures for the clustering problem. Now, and it turns out, because you might wonder actually about it, it turns out that actually the right value of alpha really depends on the data set, on the distribution of a clustering problem that you have at hand. So just to give you a couple of quick examples to illustrate this. So, for example, for these clustering instances, for this clustering instance on the left, right, where we have two target clusters, the two concentric circles here, the red cluster and the blue clusters, it turns out that single linkage will do great because it will always find the smallest gap in deciding what to merge next, so it will never mistakenly connect a red cluster and the blue cluster. So single linkage works well on this instance on the left. However, complete linkage, which tries to keep the diameter of the induced cluster in the hierarchy as small as possible, it will do badly on this instance. You show that it will have higher on this instance. So this is an easy instance for single linkage, but a hard instance for complete linkage. The one on the left. Now the instance on the right, it's actually an instance that is hard for single linkage. So in this instance, we have these two disks, the green, purple, and the green disk and the purple disk. Turns out that if you look at it, this will be hard for single linkage, but it will be easy for complete linkage. Right? So here is, I have on this slide two examples where alpha 0 is best. One where alpha 0 is best, this corresponds to, we should be using single linkage, and one where alpha 1 is best corresponds to, we should be using complete linkage. But in general, really, the right value of alpha can be anywhere between 0 and 1. And we really want to learn it based on data. And I'll come back to this point later. I'll show you graphs later about this aspect. Okay, so it really makes a difference if you tune the parameter alpha with respect to distribution of a clustering problem. So the question is what we can prove formally. Okay, and for such family of algorithms, we are able to actually obtain strong provable guarantees. In particular, we are able to show that the pseudo-dimension, this intrinsic learning theoretic measure of complexity, is not, for this family, is quite small, is only logarithmic in n, where n is a number of input points. And this is great because then it implies you only need a very small number of samples to generalize and to get good sample complexity. Okay, so that's one positive result we have here. And we also can show here that given a sample of typical instances, we can actually find the best algorithm from this family very quickly in polynomial time. Okay? The key challenge in this context is similar to what I mentioned before, is that small changes to the parameter of the algorithm, small changes to the alpha parameter really can lead to radical changes to the tree and the final clustering produced. Okay, and intuitively it's clear here why, because a single change to an early decision made by our linkage procedure can really snowball and then produce a large change later on. Okay, so that's a key challenge here. The cost function will have many sharp discontinuities, but nonetheless, we are able to show that we can still generalize, that the intrinsic complexity of this family of algorithms is quite small. And at the high level, the key, I want to point the key reason for which we are able to obtain small sample complexity and to show that the intrinsic dimension is small is this fact. If we fix an instance and vary the parameters of the problem, as we discussed, we're going to get sharp transition boundary in the cost function. But the good news is that you can prove this can only happen at most, roughly speaking, n to the 8 times, only a polynomial number of times. Okay, and very at a high level speaking, what are these? Why is this true? Because any such sharp transition boundary will going to correspond to a root of a linear equation, where intuitively speaking, we prefer to merge one pair of clusters with another pair of clusters. Okay, so the roots of linear equations are really defined by 8 points, and there are at most n to the 8 such roots. Okay, and then this then really implies that we can only get an exponential number of behaviors by algorithms in our family only on a small number of instances, log n instances, and this then implies that the intrinsic complexity of this family of algorithms is small, so that's why you get good sample complexity. Okay, so this is the high level, the proof of why we can get generalization guarantees for this algorithms family. And I also, as I mentioned, for this family of algorithms, we can also show that we can find the best algorithm from the family in polynomial time. So the best value of alpha in polynomial time. Okay, and how do we do it? Well, given our set of typical instances, we solve for all the alpha intervals or for all these critical points over the sample, and then we just find the alpha interval with the smallest average empirical cost, average cost over the set of typical instances. Okay, and for this, how do we solve the first step efficiently? We're going to just use depth first search on an execution tree that somehow compactly describes all the possible merges over an instance as we vary the parameters alpha. So we have an efficient way to also to do all of these steps quite efficiently, which is then great because then we can also run the corresponding procedure on real-world data sets and see how well they perform. Okay, and here is a slide summarizing the findings on the data sets that we looked at, on some of the data sets that we looked at. Okay, so first of all, so here, I'm just going to give you like a quick taste of the experiment, right? So here we are looking at distributions of our clustering problems coming from classic data sets in machine learning, like MNIST, Omniglot, and so on. And here we are plotting. See here in these plots, the x-axis corresponds to the mixing parameter, to the value of alpha, and the y-axis corresponds to the average empirical loss. So the smaller, the better. Okay, and each plot corresponds to a different distribution of our clustering tasks derived from these well-known data sets in machine learning. Okay, and we can observe several things here. So first of all, really the optimal parameters really vary across different distributions. So for example, what's optimal for MNIST is alpha 0.87, but for the different distribution called ring of a clustering problems coming from the rings, this example, the alpha equal to 1.79 is optimal. So really the optimal parameters vary drastically across different distributions. And also choosing the parameter, choosing the right parameter really can lead to large improvements in accuracy, like in this example with rings and disks. And of course, another key observation here is that really we can get improvements over the classic criteria like single and complete linkage by interpolating between them in the way we do. Okay, so this really shows that this is a great idea to do in practice as well. And the good news, we also have formal theoretical guarantees for this approach. We can have proven guarantees for our algorithms. Now, I want to quickly mention that in addition to learning the linkage criteria, in our most recent work on this topic, we also were able to learn not only the linkage criteria, but also the distance function. So for example, this is relevant for situations where we have different types of input, very different types of input distance metrics. So for example, if we're clustering captioned images, we might have a distance function based on the pixel information, but we might also have a distance function based on the caption information, right? And so we might want to leverage both of them because they could be very complementary. And we can put down a parametric family of algorithms that interpolates between these distance functions, and then we can put down a parametric family of clustering procedures, so we have multiple parameters, one for the linkage criteria and one for the distance function. And again, we can prove strong proval guarantees for these and strong bounds on sample complexity and also efficient algorithms. Okay, and now I'm going to quickly mention some other applications that we're able to analyze in this data-driven approach. For now, it's still in the context of clustering problems. We also analyze the very different family of algorithms of clustering procedures that is, again, very widely used in practice. These are called Lloyd's methods or the classic K-means algorithm, which is like it's greedy. You first pick a set of centers and then you do local search to improve the clustering. And here we looked at parameterized ways to initialize the Lloyd's method, and we show how you can learn the best initialization for your type of distribution over instances. So this is again another kind of family of algorithms we look at is we look at the partitioning problems that can be written as integer quadratic programs, like the max cut problem, finding the max cut in a graph. And here we looked at the family of algorithms that are actually quite well known in the theory of computing. So not so much in practice, but very well studied in the theory of computing, where we first do a semi-definite programming relaxation of the problem, and then we do a randomized rounding. And here we consider parametric families of rounding schemes, and then you learn how to round for our types of problems, our distributions over instances. Okay, so this is for kind of clustering and partitioning problem. Now going to survey some of our other results, going back to very different types of problems, like the Lyman problem coming from computational biology. Here we analyze the generalizability of, or the simple complexity of when we're trying to learn a dynamic programming procedure. So we look at the parameterized families of dynamic programming procedures relevant to a Lyman problem, and we again analyze how we, the sample complexity of this problem. We also looked at in a very different application in the context of, we looked at branch and bound techniques. So these are widely used techniques in artificial intelligence and in operations research for solving mixed integer problems. And here a key choice is how to branch, what variable to choose to branch on. And again, we showed you can learn how to branch with provable guarantees. That's a key point. And it's another application, again, in a very different context. We looked at learning how to, we looked at automated mechanism design for revenue maximization. So here we looked at parameterized families of VCG auctions or posted price mechanisms, a large variety of parametric families of auctions and pricing schemes. And again, we analyze their intrinsic sample complexity. And also more recently in a NeurIPS 2021 paper, we are also looking at learning, going back to machine learning, and we are looking at learning a semi-supervised learning algorithm in this data-driven way. Okay, and the key fact I want to point out, because I listed all these applications, turns out that the key fact in all of these applications from a foundational point of view is that they share a common structure. If we fix an instance that we've seen in the clustering problem case, if we fix an instance and vary the parameters of the problem, we get a piecewise structure function. Okay, so just to give you one more example, for example, here, like pictorially speaking, so from the context of mechanism design, right? I mentioned one family of algorithms that we look at, that we analyze is posted price mechanisms, right? What does it mean? We have as input buyers with their preferences of subsets of the items, right? And our goal is to set prices on the item to maximize revenue. And how do we do it when we have posted prices? Well, we set the price per item, and then we let the buyers come in an arbitrary order and buy what they want at the current prices. Okay, so it's, this is what the family of algorithms does. Now, it turns out that for this family of algorithms, if we want to analyze the sample complexity, how many typical instances do we need to generalize to get posted prices that generalize on new instances? The key fact when we look at the proof is, again, this like this piecewise structure, right? If we fix an instance of the problem, in this case, if we fix an instance of the problem and vary the parameters, so in this case, the parameters will be multidimensional. So it's the number of items, because we can set the price per item, right? So if we fix an instance of the problem and vary the prices that we put over the items, we can partition this parameter space with in a nice way of hyperplanes, so that inside each of the part induced by this partition, the revenue function is linear. So in other words, this dual function, fix an instance of the problem, vary the parameter, is piecewise linear in this case. Okay, and this really turns out to be true in all of these problems that I mentioned, ranging from clustering to mechanism design to learning how to branch to learning how to align sequences. In all of these problems, it turns out that to provide sample complexity, this structure appeared, right? Where it turns out that if we fix an instance of the problem, vary the parameter, the corresponding is what we call this dual function is piecewise structure. It doesn't have too many pieces, this dual function, and these pieces are given by nice boundary functions, and inside of the piece were again structured. And this then can be used to write a general sample complexity theorem that is applicable to all these problems, and hopefully it's a recipe for your favorite data-driven algorithm design problem. So if you have a new application domain, you're thinking to apply data-driven algorithm design, you want to know how to analyze it, I think this general sample complexity theorem that I described pictorial on this slide will help you. Okay, cool. And I guess I don't have too many more minutes left. So I just want to very briefly and at a high level mention that in our work, we also looked at a different formalization of the data-driven algorithm design problem, and this is the online learning formalization. Okay, and here I'll just mention at a high level. So far, we've considered the distributional or batch learning setting, where we assume that our collection of typical instances is given upfront to us, right? And but what if they come online one by one? Then we can kind of use online learning formalization to talk about this setting. And then I'm going to skip this animation. So we can use an online learning formalization to address this setting. And then formally what we want to prove is low regret. We want to show that we have a meta-learning procedure so that our cumulative performance is comparable to the performance of the best parameter in hindsight. Now, so we can use the online learning formalization. The challenge is that these scoring functions that we've seen already, they can have many sharp transition boundaries, many discontinuities. So we cannot apply classic online learning theory. And in fact, once you have sharp discontinuities, you are not even able to achieve this no regret or low regret guarantee. And so really the main contribution in our work is to identify general properties of these cost functions coming from data-driven algorithm design that allow us to achieve no regret. And at a very high level, intuitively speaking, pictorially speaking, I just want to show the picture. What we identify is that in many of these cases, the cost functions can have many sharp transition boundaries, but they are dispersed in the sense that if I look at any small ball, it doesn't contain too many boundaries of this, doesn't contain boundaries of too many of these cost functions. Okay, and then this is crucial to then show that kind of classic online learning procedures can be proved to kind of achieve small regrets. So we get a vanishing regret as t goes to infinity. Okay, and so that's nice. And again, I'm going to skip this. And we also actually just to mention again at a very high level. And so as I discussed, we are able to show that if the cost functions coming from the data-driven algorithm design context are dispersed, the boundaries, the discontinuities are not concentrated, and we can show no regret. And we also kind of in our most recent work, we kind of provide kind of general recipes for we can achieve no regret. A sufficient condition there is when the input instances are somehow smoothed. And again, to kind of come up with this general sufficient condition, we exploit the fact that these sharp transition boundaries have some structure. For example, there are roots of polynomials, as we've seen for the clustering problem in general. You know, in multidimensional, there are just zero sets of multivariate polynomials. And this can then be exploited to provide sufficient conditions for when the discontinuities will be dispersed. Okay, but to summarize, because I really don't have much time here left, just at the high level, we can extend tools from learning from online learning theory here in order to also talk about data-driven algorithm design as an online learning problem to address the case where the instances, input instances are coming one by one. Okay, great. So to summarize, I want to go back at the higher level. So my talk was about data-driven algorithm design. As I discussed at the beginning, and as hopefully convinced you from my talk with the couple of examples I had, you know, data-driven algorithm design can help us overcome major shortcomings of classic algorithm design because we can have the algorithm adapt to our domain, to our problem domain at hand. So it's very natural, you know, for many problems like clustering problems, pricing problems, and so on, we have many different types of techniques that we can use for the given problem, and really in practice, different methods work better in different settings. So it's very natural to try to use machine learning and to an instance of the problem coming from our domain to learn an algorithm that does well for our given domain. Very natural. This has been already used. Idea has been already used across different fields. But our work, what we do in our work, we are able to lay foundations, like to provide. We are able to kind of talk about approval guarantees for these data-driven algorithms. Right? So we really lay our goal is to lay data-driven algorithms on solid theoretical foundations, because of course, then the hope is that we can get even more practical data-driven algorithms. And to do so, we look at a variety of case studies, and based on these case studies, we kind of abstracted out general analysis principles. Most of them, like all of them, are about the structure of these dual function classes. And as I mentioned at the beginning of my talk, basically this line of work also really expands, I think, not only the frontiers of algorithm design and analysis, but really the frontiers of machine learning, because we end up learning objects that are much more complex than we typically learn in machine learning. Like we often are concerned with classifiers in machine learning, predictors. But here we're really just learning algorithms, right, which are more complex objects. And the corresponding loss functions are much more tricky. Like, you know, they have many sharp transition boundaries. So we also push the boundaries of machine learning here as well. And just to also end on a kind of a higher note, on a high-level note, I want to just point out that, I think that this data-driven algorithm design approach, generically speaking, can help us to somehow long-term, maybe we'll be able to, by using it, we'll be able to somehow get new algorithmic paradigms, right, of the type that humans are not able to design by hand, in any way. So, maybe we can, maybe long-term we are able to use data-driven algorithms to discover completely new algorithmic paradigms from what we are currently used with. And maybe also proof techniques, to discover proof techniques for the correctness of those algorithms. Great. So I want to just end my talk by saying that I have the references for the papers from my group that I presented in the talk are here on this slide. I, of course, want to acknowledge all my collaborators, my students. Many of my students have worked on this. And this work has been done with many collaborators. And so the references are here on the slide. And I want to, of course, thank all of them, particularly, of course, my students, but also all my collaborators. Thank you.
Okay, thank you, Nina, for this really interesting and clear presentation. I'm sure everybody enjoyed that. I think we'll now move on to the audience questions. There were quite a few, and I've tried to sort of distill them into some categories. So we had several questions. I think this is a really interesting one about the choice of the family of algorithms to start with, whether there's a way to be sure that it contains an algorithm with good performance. So it's like generally, are some of these problems such that we can know ahead of time that there's a good one in the family, or is it more like in machine learning where there's a sort of an art to guessing a good family to start with?
Okay, so that's a fantastic question. So can people see my slide if I go back? So maybe I don't need to look at the slide. So it's a fantastic question, actually, but it's really a great question. So, right, so it's a great question. So in some of the problems that we looked at, like the clustering problem, so some of the families that we picked, like the family of linkage algorithms that we picked, actually there we had some analytical reasons to look at them. So for example, we know, and I had a line of work with several of my students, a couple of my students actually wrote PhD thesis about it, both Ingül Yang and Colin White. They wrote PhD thesis where they analyzed what clustering algorithms work well if the instances are stable, in the sense that, if you slightly perturb the distance function, the optimal solution, maybe according to k-mean, so k-mean doesn't change much. So the instances are stable. They are not worst case instances. And, but this notion of stability will have some parameters, of course, and depending on the parameters or how stable they are, you end up using one algorithm versus another. But all those algorithms that we end up deriving for stable instances are of the form we do first linkage followed by dynamic programming on the tree that we obtain. So really that kind of, that knowledge that we have that on certain types of nice instances, we algorithms of the form where we do linkage followed by dynamic programming, basically that intuition made me look, that knowledge made me look at this family of linkage algorithms followed by dynamic programming. So this is an example where we have analytical reasons to believe it's a good class of algorithms to analyze for stable instances. Okay, so there we kind of knew. But of course, in general, for some other problems, but of course, the family might not work well for worst case instances, first of all, right? And also for other problems, we sometimes don't have such, when we look at this family of algorithms, we don't necessarily have strong analytical reasons to believe it will be great for our problem. So in that case, you take more like a machine learning approach, as you said, and it kind of is more of an art to come up with a family of algorithms, but not necessarily more of an art, but what you can guarantee formally is that, you put down a parametric family of algorithms and you're going to compete with the best algorithm from the family. So you still have some guarantee. Now the question is, will the best algorithm from the family do well for your types of instances? In general, for all of these case studies that we looked at, we don't know necessarily. But, but I guess that could be a complementary research, like to understand conditions under which you can provide such guarantees.
I guess
to answer the question.
Yeah, I guess a natural follow-up would be whether there's you can do some sort of model selection where you have different families of algorithms of different complexities. And
absolutely, yeah. So that would be great follow-up work to the model selection. Absolutely, to put kind of families of algorithms increasing in kind of complexity and to do model selection, right? Definitely, absolutely. Yeah, great. We have not done that actually, but it's a great question. Yeah. So.
Okay, another category of question. We had several people asking about sort of broadly speaking, domain adaptation. So if you had training instances from certain types of domains, and then we try to use the resulting algorithm we trained there on test instances from a different domain or different types of test instances, is there anything that we can say about performance? Is there any kind of thoughts in those directions?
Yeah, fantastic question again. So one answer could be, well, like in the talk today, I presented distributional learning formalization, or all the instances are coming from the same distribution. Another extreme is where we do online learning formalization. We kind of assume that the instances can be even arbitrary, and then we get regret bounds. But of course, those regret bounds could be pessimistic because we assume that the instances are completely arbitrary. So the type of question you're asking me, what if the distribution of the test instances is close to the distribution of training instances, but not but somehow close in a certain sense, right? But they're not, the test instances are not completely arbitrary. What can you say there? And actually, we have an upcoming new RIPS paper with my students, Drabi and Misha, where we're actually able to do a meta-learning approach, right? Where we kind of define a notion of how related should be the test, kind of the sequence of problems that are asked to solve, and we kind of provide guarantees in that context. So we also looked, we have an upcoming new RIPS paper where we're able to address, it's not so much domain adaptation. We don't imagine that there is only a training distribution and a test distribution, but we are imagining we are serving a sequence of problems. So you get a sequence of distributions, instances coming from a sequence of distributions, and if they are related, we are able to leverage that to get much better regret bounds than the online learning formalization. So we also have some answers towards that question.
Oh, okay, that's very interesting.
I did not talk about it in the talk today. I'll update the slides to put the reference to that work as well. It's just very new.
Okay, that's very interesting. So I think we have actually just about run out of time for today. But I would like to thank Nina again for her magnificent presentation and these insightful answers to the questions. Also, a special thanks also to each of you in the audience for taking the time to attend and participate today. This talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen. On behalf of the ACM, Nina Balcan, and myself, Steve Haneke, thanks again for joining us, and I hope you will join us again in the future. This concludes today's talk, and thank you again, Nina.
Thank you. Thank you, everyone, for coming.